have proximal Newton that I'll do either. We'll see how much we get to it today, and then we'll spill into next time. Next week, we have the option for doing 2 advanced topics. Depending on how long we want to spend on proximal Newton, it might turn into 1 advanced topic. I mean, these are all advanced topics. 1 more advanced topic or 2 more. So I'm going to see what people prefer, because there are many things we could cover. Let's just see. Let's take a vote. The options for advanced topics after these ones, Frank-Wolf and proximal Newton, are exact path following methods, non-convex stuff, 1 lecture on non-convex stuff, or 1 lecture on fast stochastic algorithms. Okay? So let's, just going off of those names, I know that's not that much. Who wants to hear, just vote for one of those 3 as an advanced topic. Who wants to hear exact path following methods? And how about non-convex stuff? Okay, and the fast stochastic algorithms. Okay. All right, so let me just clarify. The non-convex stuff is not going to give you general recipes for how to solve non-convex problems, just so that I didn't get your hopes up. The lecture I put together, I gave this lecture last year. It's a collection of all the non-convex problems that I know of that you can solve exactly. So it would be like a, basically a survey of all these different non-convex problems that actually have global optima that we can compute. So it's not a lecture on, some kind of general non-convex algorithms. It's more of a survey lecture. So of those of you who voted for the non-convex one, how many people want to change to something else, just so I can? Okay. Well, that's only 2. All right, so it looks like in order we'll do, if we have time, maybe non-convex stuff first, and then...
Just working.
All right, great, thank you.
I'm very sorry.
That's okay, no problem.
David's about to call me if anything's
Yeah, okay. No worries. Okay, so we'll do non-convex as a priority, and then we'll do fast stochastic algorithms if we have time. Actually, I wanted to vote one more thing, which is that we could just skim through proximal Newton very quickly. So let's do that. How many people prefer to hear 2 of those advanced topics in a quick proximal Newton, or a thorough lecture on proximal Newton, and we'll just get to 1 of them? So how many people want to spend more time on proximal Newton? Okay, it's pretty grim. And how many people want to hear the 2 other ones that I mentioned? Okay. All right, so I guess we'll go through proximal Newton quickly. So let's finish up Frank-Wolf. So where we left off, the Frank-Wolf algorithm we learned last time, we thought of it as a class of methods like gradient descent, right? That or a method that's like projected gradient descent, I should say, that looks at a problem of the form minimize some smooth convex function subject to a constraint that x lies in some set C. By the way, if this freezes on me as I'm writing, I can't actually see here, so somebody should get my attention. That was the problem. So if I'm writing and it freezes, please wave your arms or something at me. So projected gradient descent, remember, we thought of it as forming a quadratic approximation to the function and then projecting onto the constraint set at every step. Frank-Wolf does 2 things different. The first thing that's different is that it replaces this quadratic approximation to the function, this local quadratic approximation, with a local linear one. And the second thing it does differently is it doesn't project this unconstrained minimizer onto the constraint set. It rather solves for the linear minimizer over the constraint set. Okay, so these are its steps. It makes a linear extrapolation of the function, and it minimizes that over the constraint set, and it basically adds, you can think about it like it adds a bit in that direction each time. These are the updates. It either takes a convex combination of where we are and this linear minimizer over the constraint set, or you can think about it like it takes our current iterate and it adds a bit in the direction suggested by this minimizer. The same thing. Okay? And these choices for these step sizes, I said you can think about them as fixed for now, but you can do them with backtracking. We'll mention it later. So that's the picture, right? So we saw that with norm constraints, the Frank-Wolf method reduced to defining this minimizer. If my set C is the set of all vectors x for which the norm of x is less than or equal to t for some norm, this S, which is the linear minimizer over the constraint set, it reduces to finding a subgradient of the dual norm. That's all that's required. We went through this kind of very straightforward train of logic. So we find a subgradient of the dual norm multiplied by minus t. That gives us the form of the update. And we just add a convex combination of this. We take a convex combination of this and the point that we're currently looking at for our update. Okay, and the key is that this is often cheaper or simpler or both than projection onto the norm ball. It's also important to say this is often cheaper or simpler than the prox operator for the norm ball. Right? Why is that relevant? Well, if you give me this problem, right, or a problem where I want to minimize some function subject to a norm constraint, the norm of x less than or equal to t, then in many instances, right, if I'm solving this problem in, say, a stats or machine learning context, I don't know an appropriate value of t, so I'm going to solve this over a wide range of t. If I'm doing that, then I really may as well think about solving the problem in its penalized form over a wide range of tuning parameters lambda. Because in either case, I'm searching for the kind of the right amount of regularization. Right? We know that any problem like this is actually equivalent to a problem in penalized form and vice versa, and we don't know the relationship a priori. It's not easy to determine. But if we're searching for the right tuning parameter, then we can do it in either form. Right? I could either solve a bunch of penalized problems over the tuning parameter lambda, or a bunch of constrained problems over t. We would just do whatever's easier algorithmically, whatever's easier. So really, we should compare Frank-Wolf to either the projection operator onto C or the prox operator for the norm. Because we would either do proximal gradient or projected gradient over, like I said, a bunch of different values of the tuning parameter, depending on whichever is easier, the projection operator or the prox operator, typically. So this Frank-Wolf update, it applies in constrained form, and it's often simpler than both projection onto the norm ball and the prox operator for the norm ball. So that's important to remember. Okay, so I'll just get to the last example we talked about. We talked about L1 and LP being easy to do for norm balls. Trace norm we went through kind of quickly, but I'll just say it again because this is an important one. This is one where Frank-Wolf sees a lot of advantages that people are starting to care about, which is that if we have a trace norm regularized problem, where this is the sum of the singular values, so say we're doing matrix completion in constrained form, that's an example of a problem you might want to solve. Then to compute the Frank-Wolf update, all we need to do is compute the top left and right singular vectors of the gradient. The gradient is a matrix in this case, right? Because X is a matrix. Projection onto the trace norm ball requires an SVD. So that's something you can look up. The prox operator for the trace norm, we also learned that, we derived that earlier in the class, that requires an SVD. Okay, so both the prox and the projection that are associated with the trace norm are much more expensive than this Frank-Wolf update, which is actually a subgradient of the operator norm, because that's the dual norm of the trace norm. Right? So if you haven't seen this kind of stuff in detail, at least it should be intuitive to you that if I asked you to compute the top left and right singular vectors of a matrix versus its whole singular value decomposition, those are very different tasks. Right? Of course, the singular value decomposition includes the top left and right singular vectors and all the rest, so it's a lot harder to do. So this is a lot cheaper in terms of the update. This is just what I said. So I said this in words. Constrained Lagrange form, we should really be comparing to both the projection onto the norm ball and the prox operator. Okay, that's just what I said. So a summary of what we saw. L1 norm, basically, both the prox for the L1 norm and projection use order n flops. Projection is a little bit more complicated than the prox operator. You can find papers that have kind of these clever order n algorithms for projecting onto the simplex or onto the L1 ball. Frank-Wolf is very straightforward for this case. It's just order n as well. So it seems like for the L1 norm, you don't really gain much with Frank-Wolf. But for the LP norm and the trace norm, there's a big difference. So in general, right, we saw that computing a subgradient of the LQ norm, which is the dual of the LP norm, say if P and Q are dual, that's still order n. We had an explicit form for that. Projecting onto the LP norm, I don't know how to do that in general. I don't think it's known. And I don't know that there's also a prox operator for the LP norm in general. I believe both of those have not been figured out, if I'm not mistaken. The trace norm, both the prox and the projection are much more expensive. Okay, so these are just 3 examples of many. Special polyhedra, special cones, sum of norms, atomic norms. All these things have efficient Frank-Wolf updates. You can take a look at this paper. I list actually 2 papers by Martin Jaggi where he gives a bunch of nice examples. So if you're curious, take a look at this. Yeah, Sammy.
What about norm form square root of x transpose q? It's a q norm.
Uh-huh.
How does so the prox operator is different?
Yeah, it's a good question. So that's actually fairly easy to do with Frank-Wolf, right? So that might be an exercise that you could compute, right? But that actually requires an inverse, computing an inverse of Q. It's closed form, but it requires the inverse of Q. So depends, I guess, if Q is structured. Good question. Okay. Yeah, so take a look at that paper if you're curious. So here's now where we're going to kind of understand the limitations of Frank-Wolf. So it's important to see these kind of examples because what we're about to show and what I mentioned at the start of the lecture or the start of the Frank-Wolf part last time was that Frank-Wolf appears to have, when we write it down, the same convergence rate as projected gradient. Right, so if I tell you that it has the same convergence rate and each iteration is much cheaper computationally, it seems like we'd never want to use anything else. Or we never want to use a first-order method in place of Frank-Wolf. Well, when you run examples, here's an example, you can actually see that in practice it has a slower convergence than first-order methods. Okay, so even though it gets the same rate, even though it has in principle a 1 over epsilon rate, which we're going to show, or I'm at least going to state, practical examples show that actually each iteration makes less progress in terms of convergence to high accuracy. So all I did was I took a constrained lasso problem, medium-sized problem, 500 variables and 100 observations, and I ran projected gradient and conditional gradient. In other words, the Frank-Wolf algorithm. And I used this fast projection operator onto the L1 ball, although it doesn't matter because I'm measuring it per iteration here. But you can think about on each iteration of Frank-Wolf and of projected gradient, they both are order n, and they're both pretty similar computationally. And we can see, first of all, what's the first thing we see? Frank-Wolf is not actually a descent method. Okay, these are not numerical accuracy problems. It's not a descent method. You can see that in many examples. So it's called conditional gradient method. The second thing we see is that it has a lot of trouble getting to the high accuracy regime. I mean, we already know that if I were to plot a second order method here, then it would dominate all of these. But even compared to projected gradient, Frank-Wolf appears to be struggling. Okay, so it's somewhere, I guess its practical speed appears to be somewhere in between something like a subgradient method and a projected gradient method. And an important caveat is that I use fixed step sizes here. So I use the gamma equals 2 over k plus 1. Line search would have helped. But in my experience, I also use a fixed step size here for projected gradient. So in my experience, if you give them both the ability to do backtracking, then the same kind of rough comparison still holds. So before we talk about the convergence rate, let's talk about a very important property of the Frank-Wolf iterates, which is that they admit a very natural duality gap. So it's actually a suboptimality gap, but I'm calling it a duality gap for a reason. And this is something I think that it could have been known earlier, but certainly in Martin Jaggi's PhD thesis, this was featured very prominently. So at least I'll attribute it to him for now. So basically, remember our Frank-Wolf problem is to do the following. Our updates are to compute the argmin of the gradient of f of x transpose s for all, I guess, yeah. This is the problem we solve. And I can also write that, right? There's no loss of generality if I were to look at it like this. It's the same problem. If I ask you to minimize the inner product with the gradient, it's the same as maximizing the negative inner product, and this is just a constant. So it's really the same way of writing it, just slightly different formulation. Right? I'm looking for the argmin or the argmax. That's why these are all equalities. So this is the Frank-Wolf update. We know how to compute this. It turns out that actually this quantity, the max, not the argmax, just the max is a duality gap. So in other words, if I look at f of x minus f star, that's smaller than or equal to this quantity. So it's a very important property of the Frank-Wolf iterates, right? Because we're computing this all along, so this is something that comes for free, basically. We don't have to work at all to find a valid suboptimality bound or duality gap. So how do we see this? I have the proof on the slides. It's basically 2 lines. So let's just recall that the first order condition for convexity, right, for f to be convex, say at the point xk minus 1, is that if I take any other point and I look at the value of f at that point and also the value that would be assigned to that point under the linear extrapolation around xk, then the linear extrapolation is an underestimator for the function, right? So f of s is bigger than or equal to f of x plus the gradient of f of x transpose. I don't know why I have y here. I'm sorry, there's a typo. This should just be an s minus x. Okay? If I minimize both sides over all of the points s in the set C, this is true for all points, right? So if I minimize over all s in the set C, then the left-hand side gives me f star. And the right-hand side gives me basically this f of x plus the minimum of the gradient transpose, this should say s minus x. If I rearrange this, then it gives me exactly this statement right here, that the duality gap, so if I look at f of x minus f of x x star, that's less than or equal to minus the min of the gradient transpose s minus x, which is the max. Okay, so this thing, if I just move this to the other side and move f star to this side, it gives me this statement here that I wrote down. So why do we call this a duality gap? This should now be something that you can see, at least in a high level, without having to think about too hard from our work on duality. Well, if we rewrite the original problem as an unconstrained problem, but with an indicator function, f of x plus the indicator of x lying in the set C, then we can think about its dual. Think about the dual problem. And from our work on duality and conjugates, we know that if we have a sum of 2 functions, right, f of x plus g of x, and I ask you to derive their dual, then you should be able to do that at least in terms of their conjugates without thinking, because this is a kind of a generic rule we learned. I just take the conjugate of one function and the conjugate of the other, and it's a max problem, and it's the maximum minus conjugate of f minus the conjugate of the other, and I evaluate one of them at, say, minus u, and the other one at u. This is this kind of rule we learned. So I'm just reading off that rule. This is the dual. If this is an indicator function, its dual is the support function, another thing we learned. The dual of an indicator function is a support function, right? The support function of a set. So the indicator function of a set, of course, just to remind you, it's either 0 or infinity. Something we learned in our lecture on duality. Conjugates, the dual of that is the support function, and vice versa, which is the maximum inner product, say, of over all y in the set C of y transpose x. So now I can write down the duality gap, literally, between these two problems at the point x and at a point u. I'm not telling you which dual point to use yet. So I'm subtracting this criterion from this one. That is literally the duality gap. If I had a dual point x and primal point x and a dual point u, that would be f of x plus f star of u plus the indicator function, the support function of minus u. If x is primal feasible, then this should be 0. Right? So we're going to actually evaluate at a point x in C. So that doesn't appear. And we're going to use now what we called Fenchel's inequality, which is that f of x plus f star of u is bigger than or equal to x transpose u. That's what we called Fenchel's inequality. That's true for any points x and u. It also comes directly out of the definition of the conjugate function. So if you've forgotten all of this stuff, then go back and look at it. It should make sense. All these calculations should make sense. And therefore, the lower bound of the duality gap is this. Right? It's x transpose u plus the indicator the support function, evaluated at minus u. And if all I do is I evaluate this point at my current iterate, and I take as the dual point the gradient of f at x, then this is going to give us exactly the claimed gap. Right? If we stick in x transpose the gradient of f of x plus the support function evaluated at the minus gradient, which is the maximum over all s in the point C of the minus gradient transpose s, then this is equal to the maximum over all points s in the set C. It doesn't matter, I can put that in the max just to make it clear, which is the gap that we claimed. Okay, so this duality gap, this gap we can actually think of as a duality gap for this logic. That's why we say duality gap. Okay, so two different ways of seeing that it's going to give us a bound on the suboptimality of our function at the current iterate. So now we know how to stop Frank Wolf, right? That's one way to stop it. You can think about the iterations proceed as follows. Right here, compute this. Compute actually now the gradient of f at xk minus 1 transpose xk minus 1 minus sk minus 1. That's the duality gap. Stop the algorithm if that's small, otherwise make the update. So just stick in a stopping rule right there based on the duality gap. So here's the convergence analysis that I wanted to mention. And I have part of the proof in the slides. For the rest of the proof, it's very straightforward. And you can take a look at the papers I referenced for it. The proof depends on something that Jaggi calls the curvature constant. So it's defined as follows. I look at all triplets, x, s, and y in the set C. Or really, I'm just looking at all points x and s in the set C. And every y that lies on the convex combination between x and s. So take any 2 points and take the line segment joining them. And what you compute is the difference between f of y minus f of x and this gradient term, the gradient of f of x transpose y minus x. Okay, along that line segment. Basically, the maximum difference along that line segment, and it's just scaled for no reason by 2 over gamma squared, where gamma is this. Well, this is for a reason. It makes the curvature constant scale well in the proof, but it really depends critically on this quantity. Let's try to debunk this in a few ways. First of all, is this always positive? Is m always positive? Or let's not even think about m. Is this quantity always positive in the inside? So I want to know, is this true? F of y minus f of x minus the gradient f of x transpose y minus x. Right. It's always positive because, well, at least when f is convex, which what we're assuming, it's always positive. Because if I rearrange this, it just says that f of y is bigger than or equal to the linear extrapolation given by f. Okay, so that's good. I'm sorry, there's another typo here. It's supposed to be m. When f is linear, if f is a linear function or an affine function, then it's equal to its linear extrapolation. Right, so this curvature constant would be 0 because every term would be 0 in here. So it's a measure of how curved f is in some sense. Right? If this is bigger than 0, then f is curved. And if f is extremely curved, then this is going to be very, very large. It's the maximum kind of curvature in some sense, maximum departure from linearity. This is the departure of the function from its linear extrapolation around x. This is also called the Bregman divergence. I don't know if people would have seen that in other classes, but this ends up being a very important quantity in many different contexts, even in optimization. This, and maybe in another semester we might talk about mirror descent. I chose not to talk about it this year as an advanced topic, but mirror descent kind of relates to some of this stuff, and it depends critically on this quantity we call the Bregman divergence. Okay, so think about this, like I said, as a measure of curvature of the function m, f, over the constraint set C. And with that in mind, let's just kind of go through this result. If we use the fixed step size choice, gamma k is 2 over k plus 1, then after k iterations, we get a suboptimality bound that looks like 2m over k plus 2. Okay, so if we think of this m as a constant, then this is telling us that we get a 1 over k rate or a 1 over epsilon rate, depending on how you want to say it. This is really just the exact same as projected gradient. In fact, an even stronger result than this can be proved, which is done in Jaggi's paper, which says that actually if you were to compute the duality gap, then after this many iterations, you would quit. After order 1 over epsilon iterations, you would quit if epsilon was your exit criterion. So this is a statement about kind of the true suboptimality of the function, but even if you'd used the duality gap, you would have quit kind of at the appropriate 1 over epsilon rate. So it looks good, right? It looks like we should think of this as not very different from projected gradient. In fact, we can make that relationship even more precise, which is we could ask, how does it compare if you assumed that the gradient was Lipschitz versus if you assumed that the function f had a curvature constant m? How do those assumptions compare? Well, a simple calculation here, which I think I'm going to skip because we don't have that much time, but you can go through if you're curious, shows that the curvature constant of the function f, which is m, it's always less than or equal to the squared diameter of the set C. So this is the biggest distance between any 2 points in C, times L. L is the Lipschitz constant of the gradient. So in other words, if we assume that the function has a bounded curvature constant m, then it's really no stronger than assuming that the gradient was Lipschitz, right? Because it's implied by a Lipschitz gradient, as long as the diameter of our set is bounded. And if you think about this also, then you can see that the rates for projected gradient and the rates for this Frank-Wolf are actually quite similar. So let's actually think about m as, per that last suggestion, this is about 2 times the diameter squared of C times L over k plus 2. What did the rate for projected gradient look like? Do you guys remember? So it certainly had a k, either k plus 1 or k plus 2 in the denominator. I can't remember. So this was conditional gradient, or Frank-Wolf. For projected gradient, it looked like how far we were from optimality. I think there was a 2 here even, divided by the step size t times k, I want to say k plus 2. I don't know whether it's k plus 2 or k plus 1, but that doesn't really matter. T times k plus 2. By the step size, we know the maximum step size we can take that's fixed is 1 over L. So let's plug that in. You see they really match quite closely, right? This quantity, in the worst case, is going to be really the same as the diameter if we start really far away from the solution. In fact, this is an upper bound, of course, on the distance, the place where we started to optimality. There's not much difference in these bounds, but they perform quite differently in practice. So what does that tell you about these bounds? It tells you that these bounds aren't really telling the full story. You know, the rate is, it's helpful to know, certainly helpful to know that Frank-Wolf is on par with projected gradient. We probably shouldn't dismiss it, but we shouldn't think about it as being practically equivalent in any sense in terms of its convergence to high accuracy. I'm going to skip this too. If you're curious to know how it's proved, go through this slide and then take a look at the Jaggi paper. It's very simple. It's probably even simpler, or maybe it's as simple as the projected gradient proof. There's not much sophistication. Compared to what you've seen already, there's not much sophistication. It's straightforward. Here's one property of the Frank-Wolf iterates that are important to mention, which is that they're affine invariant. Very different from gradient methods. Okay, so we're seeing a lot of different properties between the two. We're seeing certainly some common things like the rate and different properties like this one. Remember that we saw that Newton's method was affine invariant, and so were things like the interior point methods should be affine invariant as well. But the gradient methods we saw certainly weren't. We know, right, that conditioning really affects their performance. This is telling us, this slide is telling us a very simple sequence of arguments. It's saying that actually if you were to take your problem and apply a non-singular transformation, then the Frank-Wolf iterates would be the same in either domain. So really, they're in the same way that Newton is, they're affine invariant. And it's fairly easy to see, just to go through it quickly, if let's define a new coordinate system x prime based on a non-singular transformation A, so an invertible matrix A. Okay, and I'll think about doing Frank-Wolf on x prime rather than on x. And I'll think about a new function, which is h of x prime, which is f of a times x prime. Okay, so in this domain, in this new kind of coordinate system, Frank-Wolf would proceed according to these two updates. It would just find the minimum, or the minimizer of the gradient of our function at our current point, transpose z, subject to z being in the proper constraint set. Well, here, since we've changed coordinates, you can check that the constraint set now is A inverse times c, right? Because in this coordinate system, you have to multiply by A to get to the previous one. So if we multiply z by A, we get that AZ is in C. So that's why, in other words, z is in A inverse C. Okay, and then this update is as before. So what we're going to claim is that actually this is the exact same update that we saw before. Right? And it's not hard to see because if we were to take the gradient of our function with respect to x prime, then we would see that actually by the chain rule, that's A transpose the gradient of f with respect to its argument evaluated at ax prime. So we basically get a gradient of f here evaluated at ax prime transpose az from the chain rule. And now all we have to do is make a variable substitution, right? Az is x. That tells us that x is in C, and it tells us exactly that this update is equivalent to what would have been made in the previous coordinate system. So it just comes from staring at that and using the chain rule. It's a very simple argument. Even the analysis is affine invariant. So this curvature constant is not going to change in this new coordinate system versus the old one. It's the same argument that I gave up here. Just use the chain rule. You'll see that basically the chain rule gives us an A, and if we want to switch back to the old coordinate system, then we would basically have to multiply this by A inverse. So they're going to cancel. So the analysis and the algorithm don't depend on, are unchanged under affine transformations or linear transformations. It's a unique quality. Another thing that's nice about Frank-Wolf is that it's pretty robust in some sense to inexact updates. So we didn't talk about this with the gradient method. I think I gave you a paper in the slides that gives you an analysis of this, but you could ask something like, what happens if instead of applying the true prox operator, I apply some approximate version of it? Okay, and there's a paper that I told you that you could take a look at that proved that you could still get the right rate under certain conditions on how bad the approximation is. That's a pretty sophisticated analysis. It's a nice paper. It's a pretty sophisticated analysis. With Frank Wolf, the analysis actually for inexact updates is it's almost trivial. It's very straightforward. And the proof is essentially the same as it was before. All that happens if we basically incur an error of delta is that we multiply the right-hand side by 1 plus delta. So in a sense, I think it's fairly robust to inexact updates. Now, when I'm saying robust, all I mean is that the analysis is straightforward. It carries forward from what it was before. I'm not telling you that I think Frank Wolf will handle inexact updates in practice any better than proximal gradient will. I don't know that, actually. That would be interesting to know. One important point is that if you look at how I wrote it, I said suppose that we, at the step k, instead of choosing sk minus 1 to exactly minimize this quantity, suppose we chose it so that it was within the minimum plus an error. That error looks like m times gamma k over 2 times delta. So m is a constant, so that doesn't matter. I could have just sucked that into delta. 2 is a constant, obviously. Gamma k is what's important here. So I'm thinking if delta is a constant that you fix ahead of time, you say I want to fix delta at 0.01, and that tells you that basically the suboptimality bound is going to be 1.01 instead of multiplied by 1. But what do you need for that to be true? I need that at every step, the kth step, I optimize to within delta times essentially gamma k of the minimizer. Well, since gamma k goes to 0, right? Gamma k looked like 1 over k. It's telling you need to be more and more accurate as the iterations proceed. So as you get closer and closer to optimality, the inexact updates have to be less and less inexact. The same is true with proximal gradient. Require the errors to vanish over the course of the algorithm. It's an important property. Two variants of Frank Wolf that I'll mention. One is backtracking line search. So instead of fixing gamma k to be that quantity 2 over k plus 1, you could use backtracking. I actually wrote down the exact line search here. I don't think there's any reason for that. You could use either. And another very interesting variant that we won't have time to talk about is a fully corrective version, which essentially after you find the point sk minus 1, remember that sk minus 1 was equal to the argmin of the gradient transpose S subject to S lying in the set C. The fully corrective version takes this, and instead of applying this update, as we learned before, which is going to be gamma, or 1 minus gamma k times xk minus 1 plus gamma k times sk minus 1. So instead of applying this update, the fully corrective version actually takes xk to be the point that minimizes the function over all points x that are in the convex hull of the points we've seen so far. So x0 all the way through sk minus 1. So each of these are atoms, in the sense that's one term people use for them, in the sense that they mark the location of the linear minimizers. We collect all those atoms and the initial point, and the fully corrective version basically allows us to choose very greedily the minimizer among this convex hull. So of course this is much more expensive than the Frank Wolf update. But it allows you to do more than just move a little bit along the convex combination of xk minus 1 and sk minus 1. Allows you to look at the full convex hull, so allow previous iterations to have some say in what happens now too. So some approximate versions of this have been studied, because this is usually typically hard to do exactly, and they're shown to perform much better than the usual Frank Wolf updates in some situations. Both of these variants have the same complexity, iteration complexity. There's still 1 over epsilon. So some things that could be interesting to pursue if you're interested in Frank-Wolf. There's another version, another variant that I'll just write down, which are called backward steps. And I think actually Jersey sent out, or somebody, maybe it was Jersey, I thought sent out an email on Piazza saying that there was a seminar on Frank-Wolf, was it yesterday? Someday this week, that talked about this variant as well. So maybe you guys can teach me about this if you went to the seminar yesterday. I think it's interesting, I just didn't include it in the slides. Basically, it allows you to move, I think, in some sense opposite to the directions suggested by the atoms. All right, any questions about Frank-Wolf before I get to this last little bit? We went through it kind of quickly, but I think the idea should be clear at least. So one way to think about it in your mind is that it's a very efficient method if you're looking for a rough solution. Its iterations are very cheap. You probably can't get much cheaper than that. And it doesn't even have the same convergence kind of properties practically as gradient descent, although it does theoretically. So if you're looking for something rough, or even as a rough solution to start up another algorithm, it's a good place to go, definitely. And if you start using things like this fully corrective version, backward steps, line search, that improves its convergence in practice. All right, so we're going to finish a few more slides on Frank-Wolf and then take a break. This is something pretty neat that came out of work after the kind of initial Frank-Wolf wave, which is approximate path following with Frank-Wolf. I think it's a really nice idea, really simple. And let's think about this norm constraint problem, which is to minimize the function f of x subject to a norm constraint on x. And thinking about this in the statistical context, say, let's suppose we're interested in the solution for many different values of t, because we're going to think about what's the appropriate amount of regularization. And then maybe we'll use cross-validation or something else to determine what properties those solutions had. So we pick some value of t given a bunch of solutions. So we're interested in basically the solution path to this problem, which means the solution as t varies from 0 onwards. And we could do that by just laying down a grid of values, right? We can choose some dense grid of values over a big range of t's and solve all those problems with Frank-Wolf or whatever our favorite method is. We could even use warm starts, and that would give us a discrete set of solutions at a discrete set of points t. But we can actually do more than that with Frank-Wolf. And unfortunately, since you didn't vote on the exact path following, you won't hear about how to do more than that in some cases by exactly following the path, but you can take a look at the notes from last year or 2 years ago. With Frank-Wolf, we can do something quite interesting, which is that we can actually calculate, in a sense, what is the next value of t that we should solve the problem at dynamically, so that we guarantee that at this current value of t and every value of t between now and the next point, the duality gap is still smaller than something we specify, say epsilon. So what we're going to produce at the end of the day is a path that has the property that at every point along the path, the duality gap is at most epsilon. So our approximate path is uniformly close to the actual solution path. It's a pretty cool thing. So you fix this parameter epsilon, which is how far you want to deviate from the solution path. Say 0.01 or something. And you fix another parameter m, which should be something that's larger than 1. Because you're going to solve inner problems at the accuracy epsilon over m. And you're going to repeat the following steps. So first, we're going to start at 0, because assuming this is a norm, if we take t as 0, then the solution is just 0. So we're going to start at 0. It's the easiest place to start. At every step, we're going to calculate what we're going to call like the next value of t, which I call tk, given the previous one, which is just the previous one plus something. And that something is 1 minus 1 over m times epsilon divided by the gradient of our loss function if I evaluate it at the previous point. So t1 is going to be given by 0 plus 1 minus 1 over epsilon times the gradient of f at 0. once I apply the dual norm. This tells us how far we can go. And then we're going to set the solution to be exactly the same for every value of t between tk minus 1 and tk. So we're going to actually produce a piecewise constant solution path. You can imagine, let's suppose that we're here. This is tk minus 1. And we have this solution x hat tk minus 1. Then we computed this next value, tk. And it was computed in such a way that we're guaranteeing that if I just were to stay where I was exactly, so I would keep the solution constant, my approximate solution constant between tk minus 1 and tk. So in other words, I set my guess at the solution to be just what I saw at tk minus 1 for all t between tk minus 1 and tk. Then I have the property that suboptimality gap is less than or equal to epsilon along this segment. So I'm not really hurting myself by just pretending that the solution is constant and not actually resolving in this interval. Now tk I have to solve again. That's what I do next. I solve again. Maybe the solution actually is this. And then I'm going to compute tk plus 1. And actually it could be that I only can move a little bit. Right, and I guarantee that if I have to keep the solution at whatever I computed for tk to be the same between these two segments, then the suboptimality gap would be still less than or equal to epsilon. And I continue doing this. So we actually don't know a priori the length of these segments, right, or the locations of these segments. These are determined adaptively at each step. And how do we get these solutions? Well, these solutions at each of these points are computed by Frank-Wolf. So each of these guys at tk minus 1, tk and tk plus 1, I use Frank-Wolf with accuracy epsilon over m. So I'm going to terminate when I have actually a more than epsilon accurate solution at these points. Is the strategy clear? Maybe not the reason why it's true, but just the strategy itself. Okay, so why is it true? It's actually quite simple. We're going to prove it on the next slide. Why is it the case that when I do this, do I get the property that if I were to keep the solution the same, is the duality gap always less than epsilon? Well, the duality gap we can compute right from Frank-Wolf. And if you look at it as a function of t, which we're going to do, you're going to see it's actually a linear function of t. And so at each of these points, I know the duality gap is epsilon over m at most. And it's a linear function of t. So as I increase t, the duality gap is going to grow from epsilon over m. And at some point, it's going to hit epsilon. So at some point, this linear function is going to hit epsilon when it starts at epsilon over m. All I want to do is I want to stop it once it hits epsilon. If I do that, then I've guaranteed that at every point between where I started off and where I am now, the duality gap is going to be less than or equal to epsilon. If I take it any farther, then I'm going to be in trouble. I'll violate my duality gap. And determining how far to go is very easy because it's a linear function. So once I know that it's epsilon over m at some point, and I asked how far I can go for it to be epsilon, it's a very simple calculation and just comes out to be this. So this is the argument here. The duality gap, remember I told you it's I'm sorry, this is another typo. I've had a few typos this lecture. This should be the maximum over all s who have norm less than or equal to t at the point t. That's the duality gap that we learned of the gradient transpose x minus s. And if I just unfold it like I had it before, this is the gradient transpose x plus, what is this? This is equal to the max of the gradient. Let's write this out so that it's clear. The duality gap is max over all s that are less than or equal to 1 of the gradient of f of x transpose x minus s. And this should be t, which is equal to the gradient of f transpose x plus this is equal to the max over all s that have norm less than or equal to t of the gradient of f of x transpose minus s. Right, but I can actually just change this with an s, because if I reparameterize and I call s v or something, right, then this becomes a v, and this becomes that the norm of minus v is less than or equal to t, but that's the same as the norm of v being less than or equal to t. Right, this constraint set's symmetric, so I could have put s or minus s here, another way of saying it. And if I look at the points for which the norm is less than or equal to t, it's the same as t times the points for which the norm is less than or equal to 1. So that's why the t comes out. And now this, you can see this is exactly the dual norm of whatever this quantity is, gradient. So as a function of t, what is it? It's linear, right? Constant, constant, and that's where t appears. So we can see that the duality gap actually acts linearly as a function of t. And so if I had some point x for which the duality gap was epsilon over m, and it increases at this prescription as a function of t, I just want to solve for when this is equal to epsilon. And if I do that, you can see, look, I'm solving for the duality gap to be equal to epsilon. You'll see that I exactly get, did I write it down here? Yeah, if I solve for this equal to epsilon, once I know that it's at epsilon over m at the point x, this is the value of t at which I get. It crosses epsilon. Okay? That's the entire argument. So if you take a look at these papers that I referenced, this one by Geeson, for example, they do it for much more complicated situations. And they actually, I think they do it in a bit of a strange way. So it may look much more confusing from those papers. It could be also the case that their path is more efficient than the one that I wrote down here. In my experience with this path, it's kind of, maybe it fits in with what I know about Frank Wolf, which is that you don't move very far because you don't have that high accuracy at any point. So the path ends up giving you these incremental advances. So it has the property that the duality gap is guaranteed to be bounded along the way, but it's actually less efficient than if you just laid down a bunch of t's and solved. Now, of course, you have a stronger guarantee than that, because you actually have a path guarantee than just a pointwise guarantee, but I have not found this to be more efficient. However, this is my kind of interpretation or my spin on Frank Wolf path following, and these ones are much more complicated. It could be the case, because I have not compared them, that with their setup, they get kind of longer steps along the path. So don't be misled if you look at these papers and they look different. Okay, that's it for Frank Wolf. Any questions? You guys have been a little quiet. I did go pretty fast, but any questions about Frank Wolf? Okay, let's take a break. We might as well start. I guess we'll just go through at a very high level what it's about. Poor Proximal Newton was voted out. It's not going to get the same say that the other lectures did, but it's honestly should be something that you understand fairly well, given that you understand proximal gradient. It's just that there are some subtleties. So if you go to apply Proximal Newton, I'd recommend you read all the slides before you go do that. Don't just use these 20 minutes to base your decisions off of. So we're coming back to proximal gradient again. Remember, we saw what kind of projected gradient, which is a special case of proximal gradient, and how we could do something else differently with Frank Wolf. This is coming back to proximal gradient again and seeing how we can do things differently. And the proximal gradient approach, remember, it looked at smooth plus kind of simple functions, both of which were convex. And it applied the prox operator of this function h repeatedly to the gradient step that we would make under G. And this prox operator is defined as follows. It's the minimizer of the problem that looks for the to minimize the square distance between x and z scaled plus h of z. So this is called the Prox operator associated with h. And just to remind you, things that maybe you should still have in your head, but you may have forgotten, the difficulty here in applying the prox only depends on h. There's nothing here to do with g, and that dominates the computational cost typically at each iteration. Okay, per iteration, that may be the most expensive thing. We typically think of it that way. So that as long as we can compute this gradient, the prox operator only depends on h, and that determines the difficulty of the problem, of applying the algorithm. And it has the same convergence rate as fully smooth gradient descent, so if we didn't have any h. And so it's good to use when the prox is efficient. That was the quick summary of proximal gradient. The motivation was that it basically minimized at every step a quadratic expansion of g plus h, plus the original h. So because h wasn't smooth, we actually don't make an expansion to it. We just make a quadratic expansion of g plus h. And in that quadratic expansion of g, you can see the Hessian we replaced by a multiple of the identity. So it's really a linear expansion plus a squared error term between z and x. What was the fundamental difference between Newton's method and gradient descent? It was that, well, think about them both in this context. They both minimized iteratively quadratic approximations. But gradient descent used this one. Didn't have any h, but it used this one. And Newton's method used the Hessian. Instead of actually using a scaled version of the identity, it used the Hessian of the function. So it was a better quadratic approximation in some sense, in terms of how accurate it was. So now you might think, what happens if in the proximal world we did the same? We replaced this by the Hessian of our function. Right? It should be the analogy of Newton to gradient descent, but in the proximal world. That's called proximal Newton method. We're just going to replace that with the Hessian of the smooth part g. And that's something that I think was a quite old idea that, again, people have revisited in some recent years. So first we're going to define what we call the scaled prox. The scaled prox, it looks very similar to what we saw before, except I put an h here instead of the 2 norm. And this h norm we're just going to define as, if you ask for the squared h norm of a point x, it's x transpose hx. So when h is the identity, this is just the L2 norm. Otherwise, it's like a Mahalanobis distance. Yeah. Yes, that's correct. Sorry. It should be an x. Right, so the norm of h norm of x squared is x transpose hx for a positive definite matrix H. This is what we're going to call the scaled prox, the guy that uses this as a measure of distance between x and z rather than just the identity matrix, or really the identity matrix over t. If we took h to be 1 over t times identity, you'd see this is actually the prox we saw before. It's a generalization of the prox we saw for gradient descent. And now we're going to do the analogy of Newton's method, but in the proximal world, which is that we're going to take a Newton step with respect to g. So I've just written its Hessian as hk minus 1, just for simplicity. And then we'll imply the scaled prox. So again, defined in terms of the Hessian. And then we'll perform the usual update. Okay, and the step sizes here we're going to choose by backtracking. So we're going to update x in the direction given by this proximal minimizer. And as with Newton, a tempting choice is to take the pure step size, tk equals 1, but that doesn't necessarily converge, so we're going to have to use backtracking. All right, the method clear? Okay, so let's just first check that this is indeed minimizing the quadratic approximation of g plus h, where the quadratic approximation uses the Hessian. So this was our prox problem. I just wrote it out. We're going to minimize the distance between the Newton step with respect to g minus z, measured in the h norm squared, plus h of z. So remember, the h norm is just this transpose h times itself. So when we write that out, you can see, well, first of all, the term that depends only on g of x we can throw out because it's the minimum over z. The term that looks like the cross term between these two we're going to have an h times an h inverse, and that's going to cancel, so it's going to give us the gradient transpose z minus x. And the term that looks like x minus z, when we expand it, is going to have an h in between, given the nature of this norm. So we'll get z minus x transpose h z minus x, and h of z stays there. So this is indeed a quadratic approximation, where instead of using the identity here, we've used the Hessian. So when h is 0, of course, this gives us the usual Newton update. So it's like the relationship between proximal gradient and gradient. You can think of it as a generalization to Newton. When h is positive semi-definite, you can check that this prox operator, which we denote by prox h, and I think I said we'll call the scaled prox, it has many of the nice properties as the usual prox operator. So it's non-expansive. You can think about it like a generalized projection. It inherits a lot of these properties. One very kind of simple one is that it's well-defined. And we have to even make sure that it's well-defined. Is there a unique minimizer here? Well, that is the case because when h is positive semi-definite, this is strictly convex. This term is strictly convex in Z. So strictly convex plus convex is going to give us a unique minimizer. And here's an interesting kind of twist on what happens in proximal Newton. The difficulty of the prox is mostly to do with h. Right? It's mostly the case that h is going to determine the difficulty here. However, the smooth part still plays a role, and that is it plays a role through its Hessian. So the structure of the Hessian could actually influence the difficulty of this subproblem a lot. So with a gradient, when we were using the gradient was sparse or dense. It didn't matter. Really, the prox didn't change in difficulty for proximal gradient. Now we're looking at the gradient and the Hessian. And the Hessian is serving as kind of the quadratic form in this problem. So this is minimized a generic quadratic, an arbitrary Hessian in some sense, plus a linear term, plus a non-smooth function. And now, if h is structured, this may be much easier than when it's dense. Certainly when h is diagonal, we know it should be easy because that's just the prox operator from gradient descent. So the Hessian of G does play a role. So not quite as black and white as it is with proximal gradient as to what makes these inner problems difficult. Backtracking, we do as we always do. We propose the update direction v, and actually, I take that back. It's not as we always do. This is going to be a little different from what you've seen before. This part looks like what you've seen before, which is that we propose a starting point, say t equals 1, and we try to check whether or not we are less than or equal to some fraction of what we get from the linear extrapolation. So alpha is just some constant here, like 0.5. Measure with respect to the smooth part. And if all we had was a smooth part, then you see this is the exact backtracking rule for Newton, these first two terms. This is Newton's backtracking rule. Now with the non-smooth part, we also add in this term, which is the difference between the non-smooth part as our proposed update minus where we are times alpha. So we're asking for a fraction of increase basically with respect to both the smooth part and its linear extrapolation and the non-smooth part. This is not the only rule that we can use for proximal Newton, but it's probably the most efficient backtracking rule that we could use because you can see throughout backtracking, we never have to recompute the prox. So if we had to recompute the prox at every inner loop of backtracking, that might be disastrous because we haven't talked about how difficult the prox is yet, but you can imagine it's difficult given the dense Hessian. And so you can see that v only needs to be computed once here. If this is not met, I just shrink t and I just compare again. There's a different way to do backtracking, which is sometimes called backtracking arc search for this problem, which requires that we recompute the prox at every step. That'll have us exit backtracking quicker. And that'll actually be completely analogous to what we did with proximal gradient. If you look at proximal gradient, if you look back at the slides, the backtracking that we did there, at every step, it had us recompute the prox. We changed it for Newton because that would have been too expensive. But you can think about either one. So now we should get to the point where we should think whether this even makes sense. Of course, we can write down proximal Newton. We can Think about it has analogous properties to proximal gradient and to Newton, and so it's this nice combination. But does this make sense to use? Our main motivation for using proximal gradient was that we took a problem that looked like this, g of x plus h of x, and we turned it to a sequence of problems where we replaced g by something like this, b minus the norm of x squared. That's what we're doing, right? Because when we're minimizing the prox problem, it's minimizing a problem that looks like this, but where I've replaced this by a constant minus x squared. And presuming that's cheap, I'm happy to do that over and over again, iteratively. And it'll give me the minimum of this. Okay, it can be easy, depends on h. Proximal Newton is doing the same thing, but it's actually turning this into a sequence of problems where we replace g by b transpose x plus x transpose ax, or A is a matrix. So it's actually not just this simple least squares quadratic, but a kind of generic quadratic. Why should we think that's any easier than this problem? Right? It may be the case, actually, that's no easier than our original problem. So proximal Newton doesn't even make sense. In general, this can be a very hard problem. It seems to kind of defeat the spirit of proximal gradient, because the subproblem is not easy for a generic Hessian. Okay, so it's an important pause to make. So this is all true. Nothing was misleading about that last slide. In fact, you can think about it. Suppose H is the L1 norm, right? A common choice. What would the prox be for proximal Newton? It would be a full lasso problem. Be equivalent to doing a full lasso problem where the design matrix was A. We know that's not easy. Right? That requires solving it with another algorithm, say, proximal gradient, as we learned, or coordinate descent, etc. So what we should hope for if we're going to think about applying proximal Newton is that the convergence rate is like Newton, which means that even though we have to solve this hard prox, we should only have to solve it a few times before we get to a very accurate solution. If proximal Newton had the same convergence properties as proximal gradient, we'd be in a lot of trouble, because we made these subproblems super hard, and we need a lot of them. Fortunately, it turns out to be the case that, as you would hope, in kind of under broad conditions, proximal Newton has the same convergence rate in terms of number of iterations required as Newton. So it's really doing something analogous to proximal gradient, but you're doing something in a very different regime. You're solving pretty hard subproblems, where each subproblem is given by a quadratic expansion, but because you've used the Hessian properly in that quadratic expansion, you only typically need very few to get an accurate solution. So in other words, you need to only solve the prox a handful of times in order to get the accurate solution. And you really should be relying on the fact that you have a good algorithm for the inner prox. Right? You would never apply this if you didn't. So in general, it shouldn't be applied without care, because that inner problem, you need to think about how you would solve efficiently, because you're going to need to do it a bunch of times, but not as many as proximal gradient, on the order of Newton iterations. And there are a few well-known implementations that use proximal Newton, GlimNet and Quick. I'm not going to have time to talk about them. Just take a look at the slides if you're curious. These two things, I'd say, are pretty close to state-of-the-art with respect to their own problem that they solve. And they both use proximal Newton. OK, convergence analysis. It gets the same convergence rate as Newton in terms of outer iterations. OK, so it's log 1 over epsilon local rate. So it's a locally quadratic convergence rate. Each iteration uses the scaled prox. So that's important to remember. We're counting number of iterations here. These are the same conditions we put down for Newton. They're no different. Not the self-concordant analysis, for the original analysis. These ones right here. I'm going to skip through the proof sketch, skip through GlimNet and Quick. Let me just tell you this, which is important. So when you go to apply proximal Newton, unlike proximal gradient, your prox evaluations will almost always be inexact, right? Because the subproblem you're solving is not one that when we go to apply, we have a direct form for. Unlike proximal gradient, where we typically figure out that the prox is soft thresholding, or it's truncation, or it's something simple. Here, the inner proxes, right, the inner iterations, they require running an optimization procedure. So we're almost always faced with the prospect that we're going to have to evaluate the prox inexactly. And fortunately, if you use an accurate algorithm for that inner subproblem, it'll still retain all of the convergence properties as proximal Newton if the prox were exactly evaluated. And here is a nice example to show that just in practice. I took this from this paper on proximal Newton. Here are the two convergence plots. Let's look at the blue and the red for now. Between the convergence analysis for the exact inner problems being solved. So again, they can't really do them exactly. Here they're just solving them to extremely high accuracy. So they're not caring about computational time as much. And they're using an adaptive method which stops when you have a pretty good solution to that inner prox problem. You can see that the convergence plots overlap exactly. It's because they've been very careful here about purporting, about quitting the inner prox optimization when they have kind of an accurate enough solution, but not a fully exact solution. And in terms of time, it is a lot better too, obviously, if we don't solve the inner proxies exactly. Okay, so if you're interested, take a look at this slide. This slide will tell you a rule to stop the inner optimizations that still has a guaranteed Newton convergence rate. So if you stop the iterations when you have an approximate solution to the prox whose quality is dictated by this rule, then you're guaranteed that you'll still have a local quadratic convergence rate. All right, now we have maybe just a minute. I'll just quickly say that this is commonly done in practice when people have very good algorithms for solving those inner prox problems. So an example to keep in mind is we have very good algorithms for solving the lasso problem with Gaussian regression loss. That algorithm is coordinate descent. We talked about how efficient it was a few lectures ago. If the loss is logistic regression, so you want to solve a big sparse logistic regression problem, you cannot write down the coordinate descent steps exactly. You cannot minimize each coordinate descent step exactly. Even though your algorithm for the Gaussian case was super fast, you're now kind of stuck, even though you love all the tricks about coordinate descent. So what we do in that case, and what's done in GlimNet and other implementations as well, is that you make a quadratic approximation to the logistic regression loss that uses the Hessian. Each inner subproblem is then a fully dense lasso problem. And you solve that with coordinate descent, because coordinate descent is your hammer, and you know that it works well. Even though that inner solve is pretty expensive, it's a good algorithm for that problem, and you can solve it to high accuracy. So if you do this properly, then the whole thing will converge in, say, 5 to 10 iterations if you're lucky, because it has a Newton-like convergence once it gets to the kind of the right regime. So that's an example where proximal Newton is applied, to give you a sense of it. That's the GlimNet package that people commonly use for L1 penalized generalized linear models. In fact, the authors of that package, they're so confident in proximal Newton that they actually don't even do backtracking line search. When you go to use that package, they use unit steps, which I think is pretty surprising, but that's the implementation. They just use unit steps because it works so well. Quick as another example, if you came to a talk, one of the job talks by our ML candidates a week ago, he was one of the main authors on Quick, which does a very similar thing, but for large graphical models. All right. That was proximal Newton in 20 minutes. We skipped projected Newton, so take a look if you're interested. Next week, I guess we'll do fast stochastic stuff and non-convex stuff. And, remember to turn in your project reviews. You're supposed to be doing these project referee reports by, I think it's tomorrow night.